Now we have the owner checks vulnerability. This mode will demonstrate missing owner check vulnerability in Pinocchio programs. We've been on Anchor since, but now we'll explore the attack vectors in Pinocchio programs. Now, when a program reads data from an account without verifying the account's owner, an attacker can create a fake account with fabricated data and pass it to the program. See what we mean here. Now, this is a sample. We have a rewards program that controls a vault, a soul vault, and we have an instruction that claims reward. Now, as a as a reward program, we have membership accounts. Now, a membership account has data of active, true, and the owner rewards program. But an attacker can create a clone that has the same data, account data matching as we've taught before, but the owner now is the attacker program. If you write an instruction without owner checks, these claims will succeed. Both a true member and a fake member will succeed. How is that possible? Now let's check Pinocchio code and see what happens. This is sample Pinocchio code. This is the start where we process instruction data from the entry points. We match them to the instructions. The claim instruction first, it checks if we have all the necessary accounts to continue the instruction, then checks if the user is a signer, and now goes ahead to read membership data. But before this, an owner check should have been conducted to ensure that the account being passed in is owned by our program and not a fake account. If you check the secure part, this is the secure version of this code, you will see that an owner check is conducted here to ensure that the account being passed in is owned by our program and not some other program. So that is simply all about the owner check vulnerability. Just ensuring that we confirm the owner of the account being passed in to avoid issues. In the same vein, we can introduce signer checks. Signer checks is a similar vulnerability that happens or can happen in Pinocchio. Signer check vulnerability occurs when a program verifies that the public key is the expected value but does not verify if the account actually signed that transaction. I mean, an attacker can pass in the public key into a transaction, but that account he passed in is not the one that signs the transaction. How do I mean? Now, let's look at a vulnerable code. Now, we head over to the withdraw instruction. Here, this try function tries to deserialize the account data, the instruction data rather, that has been passed in. First, it checks if all the necessary accounts are passed in that instruction data. But we are expected to run a signer check on the owner. This is to ensure that the public key is not just passed in as an argument and the person sending the transaction is another different account. Let's look at the secure version to see how it looks like. This is the secure counterpart of that program. Now we see that after checking if the accounts are complete or enough, we check if the owner, which is this, is also a signer. This is to ensure, as I said, that the owner actually signed this transaction because an attacker can just pass in this owner, after all, it's just a public key, can just pass it in as a parameter or as an argument and sign on his behalf. But with this check in place, we ensure that the owner passed in is also the signer that signed the transaction.